alternating current fundamentals. Number 5. Reactance and electrical power.
In the last video, 3 devices which perform important roles in AC circuits were examined.
Capacitors, devices which store an electric charge in a dielectric between 2 plates, were presented. Inductors were also introduced. These devices store charges within a magnetic field. Finally, transformers were described. You saw how these devices, which are composed of 2 electrically isolated coils, can transfer energy from one part of a circuit to another through the process of mutual induction.
In this final video on AC fundamentals, the important concept of reactance will be introduced.
Capacitive reactance and inductive reactance will be explained. The differences among true, reactive, and apparent power will be described. Finally, the transmission of AC power will be explained.
Let's get started by exploring principles of reactance. Notice that the word react is found within the word reactance.
Reactance is the opposition of capacitance and inductance to an alternating current flow in a circuit. Before moving ahead, let's compare reactance to resistance. From your past studies, you know that resistance is opposition to current flow. The greater the resistance, the less will be the current for a given voltage. The value of a resistor is measured in ohms. This value is the same no matter what kind of a circuit the resistor is connected to, AC or DC. The value of a resistor does not change with frequency. That is, a 10 ohm resistor has the same resistance in a DC circuit as in an AC circuit, meaning that a resistor does not react to AC. But capacitors and inductors do react. There are 2 types of reactance for you to become familiar with: capacitive and inductive.
Let's examine capacitive reactance first, which responds to changes in voltage.
It is designated in formulas and equations as X sub C and is always specified in ohms. The 2 primary factors that determine the amount of reactance that a capacitor will have are frequency and capacitance. Let's consider frequency first. Recall from the last video that in an AC circuit, as the voltage changes both in magnitude and direction, the capacitor continuously charges and discharges over and over again. If the frequency were to be increased, the same charge would have to be moved onto the plates of the capacitor, but in less time. If the same amount of charge is moved in less time, then the current must increase. Taking this one step further, if the current is increasing, this must mean that any opposition to the current is decreasing. Similarly, the lower the frequency, the smaller the current will be. And if the current is less, this must mean that the opposition to the current is greater.
In either case, it can be said that this opposition to current presented by the capacitor is inversely related to the frequency. As one quantity increases, the other decreases by the same proportion, and vice versa.
Besides frequency, the other quantity that affects capacitive reactance is the value of the capacitance itself. The higher the value of capacitance, the greater the charge that can be stored, due to the larger plate area of the capacitor. Since a larger capacitor has larger plates, a greater charge is required. Since more charge flows during the same period of time, the current must be greater, and therefore any opposition is smaller.
So capacitance and capacitive reactance are inversely related as well. One way to demonstrate this is to compare the output of 2 different size capacitors in identical circuits.
For example, a 4 microfarad capacitor and an 8 microfarad capacitor are each connected in series with 60-watt light bulbs. Assume that both circuits are connected across a 120-volt, 60 Hz AC source. Notice that both lamps light, but the one on the left, which is connected to the 4 microfarad cap, glows less brightly than the other. The current flowing through the circuit with the 8 microfarad cap must be greater than that flowing through the smaller 4 microfarad capacitor. You can conclude then that the capacitive reactance of 8 microfarads must be less than that of 4 microfarads. This inverse relationship can be expressed mathematically with this formula for obtaining capacitive reactance. X sub C equals 1 divided by 2 pi Fc.
In order to understand this formula, it's important to introduce a new concept behind one of the variables called the rate of change of voltage. Let's look at a demonstration of this variable.
The rate of change is indicated by the slope of the sine wave at any given point. The greatest rate of change is found wherever the sine wave intersects the baseline. Notice that at this point it's moving in the most vertical direction. Conversely, the least rate of change of voltage is found at each peak of the wave, where the waveform is moving most horizontally.
The rate of change is closely linked to frequency. Let's see how.
This can be done by comparing two sine waves with equal amplitudes. The lower the frequency of a sine wave, the less slope it will have. The reverse is also true. The higher the frequency, the more slope it will have. So you can see that there is a direct relationship between the rate of change and frequency.
Now let's take a closer look at each component in the formula for capacitive reactance X sub C.
The lowercase f stands for the frequency in hertz. 2 pi f stands for the rate of change through one cycle and equals 6.28 times the frequency. The capital C represents capacitance in farads.
Let's use the formula to find the capacitive reactance of some example circuits.
Let's say that an 8 microfarad capacitor is connected to a 60 Hz voltage source. The first step in using the formula is to substitute the values. Now solve the equation. 1 divided by 6.28 times 60 Hz times 8 microfarads yields a capacitive reactance of 332 ohms. What happens if the frequency is doubled to 120 Hz and the capacitor remains at 8 microfarads? Once again, substitute the values into the formula. 1 divided by 6.28 times 120 Hz times 8 microfarads yields 166 ohms. When comparing the two solutions, notice that doubling the frequency reduced the capacitive reactance by half. Try one more variation. Bring the frequency back to the original 60 Hz, and this time imagine that the capacitance is doubled to 16 microfarads. After inserting these values into the formula, you'll find that the capacitive reactance, once again, equals 166 ohms.
These calculations demonstrate that increasing frequency or capacitance will decrease capacitive reactance, which, remember, is always specified in ohms. Let's compare the waveforms of the voltage and current in an ideal capacitor when connected to an AC source.
While in the last video you saw that voltage and current in a resistive circuit are in phase with each other, there are phase differences between voltage and current in reactive circuits. Graph paper will be used. The voltage in a capacitive circuit takes the form of a sine wave if the applied voltage is AC. Remember, the greatest rate of change in a sine wave occurs when it intersects the baseline at 0, 180, and 360 degrees. On the other hand, the least rate of change occurs at 90 and 270 degrees.
Now let's graph the sine wave for current.
Recall that the capacitor current will be at its maximum when the rate of change of voltage is at its maximum. Since the greatest rate of change in a sine waveform occurs when it passes through the baseline, then the maximum capacitive current will be at these points. Place a dot on the graph to mark each of these points. A different amplitude has been arbitrarily selected for the sake of visual clarity. Since the least rate of change in a sine wave occurs when the voltage is at its maximum positive and negative values, then the minimum capacitive current will take place at these points. These are also marked by dots. These concepts can be depicted graphically as shown here. Now connect the dots. Since the current reaches a peak at 0 degrees, but the voltage does not peak until 90 degrees, these AC waves are said to be out of phase. There is said to be a 90-degree phase difference between the two waveforms. A phase difference is the time in electrical degrees by which a waveform either leads or lags another. In this case, the capacitive current leads the applied voltage by 90 degrees.
By now, you should have a basic understanding of capacitive reactance. If you have any questions, stop the video here and review this section one more time. Let's examine a second form of reactance, inductive reactance.
This type of reactance is the opposition of inductance to an alternating current flow in a circuit. As you saw in the last video, when an inductor is connected to an AC source, the current is changing continuously. The counter-electromotive force that is induced within the coil opposes the tendency for the circuit current to change in magnitude. This opposition to changes in current in a coil is called inductive reactance and is designated as X sub L. The amount of inductive reactance presented by any particular coil depends primarily on two quantities: frequency and inductance. As you saw with capacitive reactance, there is a mathematical relationship among these three quantities that is represented within this formula. X sub L equals 2 pi F times L. 2 pi F represents the rate of change of the current, where the frequency F is in hertz. L in the formula is equal to the inductance in henries.
Let's solve some problems using the formula to better understand inductive reactance. First, the frequency will be altered.
Since an inductor is simply a length of conductive wire that has been wound into a coil, you can assume that its resistance is 0 ohms. In this example, the inductor, represented by this inductor substitution box, is a 0.4 Henry coil. The frequency of the voltage source will be 60 hertz. Substitute these values in the formula for inductive reactance. Now work the equation. The inductive reactance, X sub L, equals 6.28 times 60 hertz times 0.4 henries.
Remember, your answer will be in ohms.
Solving the equation, the inductive reactance equals 151 ohms.
Let's try another example, keeping the inductance fixed at 0.4 henries. But this time, the voltage source frequency will be doubled to 120 hertz.
Once again, substitute the values in the formula. 6.28 times 120 hertz times 0.4 henries yields an inductive reactance of 301 ohms. Looking at the two solutions, notice that doubling the circuit frequency doubled the inductive reactance. This is a direct relationship. Because of this, if the original frequency of 60 hertz is reduced by half to 30 hertz, then the inductive reactance will also be halved to approximately 75 ohms.
The same relationships will hold true if the frequency is held constant and the inductance changed. As the inductance is doubled, the inductive reactance is doubled.
For example, you've already calculated that with a frequency of 60 hertz and a 0.4 Henry coil, there will be an inductive reactance of 151 ohms. By increasing the inductance to 0.8 henries and completing the calculations, the inductive reactance is doubled to 301 ohms.
As you can see, The correlation between frequency, inductance, and reactance can be summarized by saying that the inductive reactance varies directly with both the frequency and with the inductance of the coil. But now let's compare the waveforms of the voltage and current of an inductor in order to better understand their relationship.
Once again, graph paper will be used. The current in an inductive circuit takes the form of a sine wave if the applied voltage is AC. Remember, the greatest rate of change in a sine wave occurs when it intersects the baseline at 0, 180, and 360 degrees. Remember, too, that the least rate of change occurs at 90 and 270 degrees.
Now let's compare this with a voltage curve.
Since the counter EMF that is induced in a coil increases with an increasing rate of change in current, the CEMF will be at its greatest when the current is crossing the horizontal axis at 0, 180, and 360 degrees. Conversely, when the change in current is at its minimum, at 90 and 270 degrees, the amount of counter EMF induced in the coil is at its minimum value of 0. Once again, these concepts can be depicted graphically by connecting the dots. Since the voltage reaches a peak at 0 degrees, but the current does not peak until 90 degrees, there is said to be a 90-degree phase difference between the two waveforms. Remember, a phase difference is the time in electrical degrees by which a waveform leads or lags another. In an ideal inductor, the voltage is said to lead the current.
But inductors and capacitors are not used in isolation from other electrical and electronic components.
When used in combination with resistors and capacitors, for example, phase differences can be used to provide some interesting effects. For example, the color signal in this VCR is based on the phase difference between two signals. You'll learn about these in your study of advanced AC circuits.
It's important for you to have an understanding of these two types of reactance, because when you get to AC circuits, you'll see how reactance interacts with the circuit resistance in certain predictable ways, which become a critical factor in the design of circuits.
For now, keep in mind that both inductive reactance and capacitive reactance are measured in ohms, and that in the capacitor, the capacitive current leads the voltage by 90 degrees, whereas with an inductor, the inductive current lags the voltage by 90 degrees. This difference can be remembered with this memory aid, Eli the Iceman. Eli reminds you that in a purely inductive circuit, L, the voltage, E, leads the current I by 90 degrees, whereas ICE reminds you that in a purely capacitive circuit, C, the current, I, leads the voltage E by 90 degrees. As you continue your study of electricity and electronics, you will find that the concepts you have learned here will play an increasingly important role. You now have a good idea about the various roles that capacitors, inductors, and transformers perform in AC circuits, and you also have an awareness of the effects of reactance.
Just as in DC, the fact that power is drawn from a source and does work in a circuit is important in AC. Let's consider some types of power: reactive, true, and apparent power.
The power consumed in a purely resistive circuit is the product of the voltage and the current. You know this formula to be P equals I times E. However, power is a more complicated issue in circuits containing reactive components, because they not only draw power from the AC source, they also return power to the AC circuit as well. In an AC circuit containing capacitance only, for example, energy is first stored in the electric field within the dielectric. But this energy will also be returned to the source when the capacitor discharges. In a purely inductive AC circuit, on the other hand, the power that is used to build the electromagnetic field will be returned to the circuit when the field collapses. Both of these examples point out one important type of power known as reactive power. The reactive power is simply shuttled back and forth between the source and the load, so the net power consumed in a purely reactive circuit is zero.
A second type of power, true power, is the actual power used by the resistive elements in the circuit.
True power calculations are more representative of the actual power consumed because they take any existing phase differences between current and voltage into account.
In all electrical and electronic systems, it is the true power that indicates the work done in the circuit. Ideally, in terms of performing useful work, all of the power transferred to the load should be true power and none of it reactive power. But from a practical standpoint, many AC loads contain both resistive and reactive elements. True power calculations take both of these elements into account, and so are somewhat more complex than simple resistive power calculations. A wattmeter can be used to measure true power.
A third type of power, apparent power, is equal to the product of the effective voltage and the effective current. Apparent power calculations ignore any phase differences that may exist between current and voltage. And while the watt is the designated base unit of measurement for true power, the base unit used for apparent power is the volt-ampere. Let's look at an example using apparent power. Suppose that in this inductive circuit, an applied AC voltage of 100 volts causes a 10-ampere current to flow. Assuming an ideal inductor, that is, one that has no resistance, the true power in this circuit is 0 watts, since the inductor returns the same amount of power to the circuit that it draws from the source. But ignoring the phase difference, the apparent power in the circuit is found by multiplying 10 amps by 100 volts, which would be 1,000 volt-amperes. Don't forget that the volt-ampere is the base unit of apparent power. In AC circuits that may contain capacitors or inductors, the idea is to deliver only the power needed from the source to the load.
Let's see how in a reactive circuit, power is shuttled between the source and the load, but no useful work is done.
The reason for this is that power is equal to the product of voltage and current. Looking at this graph, showing voltage and current 90 degrees out of phase, you can see that multiplying a positive voltage by a positive current results in a positive power curve. A positive power curve means that power is being delivered by the source to the load. A positive power curve will also result after multiplying two negative quantities.
However, it's important to realize that multiplying two quantities with unlike signs produces a negative quantity.
When a negative current is multiplied by a positive voltage, a negative power curve results. Similarly, when a negative voltage is multiplied by a positive current, you still get a negative power curve. A negative power curve means that power is being returned to the source by the load, rather than being used by the load.
A source may be delivering large voltage and line currents, but if the load is purely reactive, no electrical work will be done.
If, on the other hand, the voltage and current are in phase, as shown here, the resulting power curve will always be positive, meaning that power delivered by the source is always being consumed by the load. The reason why the power curve is positive is because when the voltage is positive, so is the current. The product of two positive numbers is also positive. When the voltage is negative, so is the current. Remember that the product of two negative values is also positive. So in AC power distribution, the goal is to keep the phase relationship between voltage and current as close to zero as possible.
You'll learn how this is done as you progress in your AC circuit studies. But for now, let's stop here and review what you've been shown.
In this video, you were introduced to reactance, which is the opposition to alternating current presented by capacitors and inductors.
You were shown that in the capacitor, the capacitive current leads the voltage by 90 degrees,
whereas with an inductor, the inductive current lags the voltage by 90 degrees.
The differences between true power
Reactive power,
and apparent power were also examined.
The knowledge you have gained here can be applied to AC power applications as well as electronics and communications. Because of today's high technology, a knowledge of AC fundamentals is a requirement for anyone planning a career in the electrical-oriented trades. By now, you've received a strong foundation for advanced AC training.